まずは、ほら、という経緯で放送が開始されたので、勉強の続きをやっていきます。今日はサンディエゴ大学の Java の続き、6週目ですね。
You've made it to our final module where we'll talk about searching and sorting, as well as giving you the opportunity to extend the project in a direction of your choosing.
今回はサーチ&ソート。間、エンドオブディス。今回のやつ講義があると、Motivate the importance of search 検索の重要さ。Let's go to perform a linear search, binary search. Explain なぜバイナリーサーチの方が、ライナリーサーチよりソーティングについて。Python data can be useful. Selection shots. Java and using the comparable interface in Java.
All right, here's your overview of the last part of the project. I'm actually only going to demo part of the last part of the project because the very last part of the project is an open-ended extension of your choice. So you'll get to have some freedom and some creativity with that. Really, anything goes. It's up to you. But for the first part of the project that everybody will do, what we're asking you to do is actually make no changes to the map at all. So your map is going to behave basically just like it did in the last part of the programming assignment. But what you are going to add is you're going to add code that will sort the earthquakes in descending order of magnitude. So when you run the program now, in addition to printing out the number of earthquakes per country, it will also print out a list of the earthquakes in the RSS feed that you read, sorted in reverse order. So strongest magnitude first, and then in descending order. And you'll write a function that allows you to control the number of earthquakes that get printed out here. So that's really it, and then you'll get to work on that open-ended extension. So have fun with it. You're going to get to learn about some searching and sorting algorithms to write this part of the project, and then dive into that open-ended extension.
Hi, my name is Nina Yi. I'm on the Google Fiber software engineering team. Search and sort are both used very commonly in the work I do at Google Fiber. Actually, don't some people use the word Google and search interchangeably? Let me Google this movie. Can you Google that recipe? On fiber.google.com, which my team works on. One of the most used features by our users is the check address button. It lets our users enter an address and check whether Google Fiber is coming to, or if it's already available in that location. Once user enters an address, the system searches through an address database of millions and millions of records to find the Google Fiber readiness status for that entered address. And the result is expected to come back almost instantaneously to the user. For that, we need a very robust and high-performing searching algorithm. Sorting is used in day-to-day programming too. For instance, to show a list of choices of something in an organized format, we sort the list before displaying what customers should choose from are displayed by Team Works on. One of the most used features by our users is the Check Address button. It lets our users enter an address and check whether Google Fiber is coming to, or if it's already available in that location. Once user enters an address, the system searches through an address database of millions and millions of records to find the Google Fiber readiness status for that entered address. And the result is expected to come back almost instantaneously to the user. For that, we need a very robust and high-performing search algorithm. Sorting is used in day-to-day programming too. For instance, to show a list of choices of something in an organized format, we sort the list before displaying them to the user. In Google Fiber sign-up web pages, the sports TV packages available for customers to choose from are displayed in alphabetical order.
これリナーサイト。いわゆる直線的。
All right, in this lesson, we're going to learn some core algorithms for searching for data. Searching for data is something you probably do every day, many times a day. And so we're going to focus on some of the fundamentals of how to search for data and how to do that quickly. So by the end of this video, you're going to be able to motivate why we want to search for data, as well as to be able to write code to perform linear search. And then we'll build on this in subsequent videos. So let's start off with a motivating example. Say I'm going on a trip, which I am. I'm going on a trip and I want to plan my airline travel. And in order to do so, if you've booked airline tickets online, you probably know that those airline ticket booking sites use a 3-letter code for the airport that you're trying to book from. So I'm coming from my hometown of San Diego, and I want to figure out what is the 3-letter code for the airport in San Diego. So there's a lot of ways I can find this information. And probably one of the most popular ways is I can go to my favorite search engine, like Google, and type in this query into Google, and Google will go off and search the information that's on the web to find me a page that will hopefully answer my question. Now, this is an example of search, and in fact, internet search is a fairly complex search, so there's a lot going on here in order to organize all the data and return me results quickly, results that I find useful, and so on and so forth. So this kind of search is a little bit beyond the scope of this course. But the idea is the same. We have a big repository of data, and I want to find some information in that data in order to answer some questions about it. This is kind of fundamental to almost everything that we do in computer science. So let's simplify the problem slightly. Instead of searching the entire internet, I'm going to take a subset of the data on the internet, a very small subset, that I can find in a file called airports.dat, which is on the website whose URL that you see here. And this file has information about almost 7,000 different airports around the world. And it's represented in terms of a number of different fields. So each line in the file has a number of different comma-separated fields. Those fields include a unique ID inside this database, the name of the airport, the name of the city that the airport is located in, the name of the country, and that 3-letter airport code, and a bunch of other information as well, which you can find out by going to that URL. So I'm going to be searching within this lesson in only this data, not on the whole internet. So what I'm going to do is I'm going to read in all of this data into my Java program, and then I'll search for a particular city that I care about in order to find out some information about its airport, like its 3-letter code. So here's the first step that I need in order to read in this data into my computer program. I need some way to represent this data. So we know how to do that. We know how to write classes and create instances of those classes. So let's do that. Let's write a class called airport, and it's going to have a field for each piece of information we want to represent about a particular airport. In this case, we'll represent a city, a country, and that 3-letter code, as well as whatever information we want to keep about our airport. Each of these fields is going to be private. As I mentioned, a rule of thumb is to keep all of our data private, but we'll provide getters so we can access each of those pieces of information. So they'll get set in the constructor when I read in the data from this file, and then I have access to all of these pieces of information for each airport that's stored in my program. So let's imagine that I've done that. I've written some code that reads in this file that has all this information about these airports into my Java program by creating one instance of this airport class for each airport in that file. I'm going to simplify things a lot And I'm going to imagine that my entire file only had 8 airports in it. So I'll read those all into each into an individual airport object, which I'm going to store in an array. So my array is going to be called airports. It's an array of references to airport objects, so one object for each airport. And what's stored in the array, again, is a reference to this object, which you see depicted here in the blue boxes. And those objects exist somewhere in your computer's memory, somewhere in the heap. And again, what gets stored in the array is the references to those objects. But this diagram is a little bit too complicated for my needs for this lesson, so I'm going to simplify things a little bit by writing all of the information from each object directly in the box for the array itself. So this is going to be my representation of the data that I've now read into my computer's memory from that big airports.dat file. And again, this is a very simplified version for the purpose of illustration. So now I've got all the data about all my airports read into my array, and now I can write a program to answer questions about the airports in that array. And in order to answer a question about a particular city's airport, I have to find that airport object first. So let's look at how to do that. So let's say I'm looking for information about the Beijing airport, and I want to find out what is the 3-letter city code of that airport, Beijing. So how am I going to do this? Well, first I need to find it. One way I can do that is just basically by starting at the beginning of my array and looking at each element in my array one after the next until I come across the airport I'm looking for, or I get to the end of my array and I haven't found it. And that's an algorithm called linear search, which we're going to look at right now. The way it works is I start at the beginning of my array, so I start at index position 0, which is the first index in my array. And then I'm going to look at the element in that index, and I'm going to ask, is this a match for the thing that I'm looking for? In this case, I'll ask, is the string to find, which is the name of the city I'm trying to find, equal to the city field in the object that's located in that array position? And in this case, I'll see that Montreal is the city in the object at position 0, and Beijing is the city I'm looking for. Those two strings are not the same, so there's no match. I'll go on to the next element in my array by incrementing index by 1. So now I look at the element in position 1. Is that a match? Compare the cities. Again, I find that's not a match, so I'll continue. Here's the index position 2. Match? Nope, still not a match. Index position 3, still not a match. Index position 4. Finally, I look at index position 4 and I see that its city is Beijing, which exactly matches the city that I'm looking for. So now I've found the airport object in question, and I can use it to answer the question of what is the 3-letter code for Beijing. So I read that out of the entry, and I can return it to my user. So this is a match, and we're done. That, in a nutshell, is the algorithm called linear search. And here's how it looks in pseudocode. So in the beginning, we initialize that index variable to the start of our array. And then we're going to have a loop that keeps going as long as we haven't found what we're looking for, in which case we just return it, or we get to the end of the array, in which case we conclude that the element is not in our array. So while our index is not equal to the length of our array, while it's less than the length of our array, we'll look at the element in the particular position where index is referencing, where index says we should look, see if the city in that element matches the city we're trying to find. If it does, we'll return the 3-letter code, thus breaking the loop and breaking the whole method, basically returning out of that method. Otherwise, we'll keep going by incrementing our index variable by 1 and going back to the top of the loop. When the loop ends, we can conclude that the city we were looking for was not in the array at all, and we return some value to indicate that we didn't find it. Okay, so now it's your turn. This is an interactive piece of the video. I want you to pause the video, and I want you to get out either a piece of paper and a pencil, or better yet, just open up Eclipse and go ahead and write the code for linear search before you unpause the video. Once you unpause the video, we'll go back over it, but I really do want you to take a shot at going back to the algorithm that you just saw, going back to the example, and writing out this code. See if you can do it. I bet you can. All right, welcome back. I hope you had a good time writing this program, writing this method. And I'm now going to write it out step by step on my tablet PC. If you really think you've got it, no problems, just go ahead and zoom ahead. You can see my solution, just check it against yours. But I encourage you to also follow me through the thought process as I write this code. So thinking back to that algorithm, the first thing that we need to do is we need to declare a new variable called index, which is going to be the variable that steps us through the array. So I'm going to do that. I'm going to declare a new variable. It's type integer called index, and its initial value is 0. So now I'm ready for my loop. And my loop is going to be a while loop. And it's going to run as long as that variable index is less than the length of my array. So airports dot length. Okay, so now inside the loop, remember what we want to do is we want to look at the airport object that's in the cell indicated by that index variable. So we're going to get that airport object out first and store it in its own separate variable just to make the code a little bit cleaner. So I'll declare a new variable, airport, A equals airports at position index. Now I'm ready to work with that airport object, and I can compare the string that I'm trying to find, the name of the city I'm trying to find, to the name of the airport that's in that object pointed to by the variable A. So I do that with an if statement, because if they're equal, I want to do something. So if my toFind equals A dot getCity. Now notice that I've used the dot equals method here instead of the equals equals operator. And that's pretty important because what dot equals is saying to Java is I want to compare the string representations in these two objects by essentially their characters. I want to know, are they the same string? I don't care if they're the exact same object in memory. I just want to know, is it the same string of characters? And the dot equals method will do that. On the other hand, the equals equals operator, that's just going to compare the references that are stored in two particular variables. And so that will only be true if those are actually the same literal object in Java's memory. So in this case, and almost always when you're working with objects, the dot equals method is the appropriate way to compare those two different objects. So if I find that the string that I'm looking for is equal to the object's city that's stored in A, then I'm going to return the airport code. So return a.getCode. Otherwise, I need to keep looking. So there's nothing really more to do except to go on to the next location. So I can say index plus plus. Notice I don't need an else statement here because if the if statement was true, then I just return out of the function and there's nothing more to be done. But if that if statement is not true, then I increment my index and I'll go back to the top of my while loop and repeat the process. Now, if my while loop completes, that means my index has gotten all the way to the end of my array and I still haven't found the city that I'm looking for. So now I need to return some value that indicates that the city is not there. And in this case, I'll just return the value null. And that's appropriate because my method is supposed to return a string, so null is a good value to indicate, hey, we couldn't find it. It wasn't there. So that's it. That's it for the code. I want to leave you, there's the code a little bit more cleaned up for you. But I do, after you're done sort of looking at and digesting the code, what I want to leave you with is a thought question. Actually, two thought questions. I want to ask the question of, if we're really unlucky, so if we're looking for some airport and it's very unluckily way at the end of the list, or it's not even in the list at all, how many airport objects are we going to have to look at to figure out either the airport code of this particular airport or to figure out that the airport's not in the list at all? So try to think of how you would answer that question in terms of some number of airports in the list. And then the more important question is, can we do better than that? Is there a way to answer this question faster? And that's what we're going to look at next.
In question that's posed, what you are using lines that are described here, O N なんて全部で N 回だから、N スクエアはソートとかに返すんだから。ってことだよね。ログ 2N が使えるバイナリーだって言った
All right, in this video, we're going to improve on that linear searching algorithm that we looked at in the last video. And we're going to talk about an algorithm called binary search. So by the end of this video, you'll be able to explain what binary search is, you'll be able to write code to implement binary search, and you'll also be able to explain what conditions need to be true for binary search, as well as explain why binary search is so much better than linear search. All right, to motivate the need for binary search, let's go back to our linear search algorithm. We were looking for airport objects that had particular city names so that we could answer questions about those airports, like what are their three-letter airport codes. And what we did was we started at the beginning of our array at index position 0, and we just marched through this array element by element until we either found the city we were looking for or didn't find it but reached the end of the array, in which case we concluded that the city wasn't there. And it worked, but I asked you this thought question at the end of the video. I said, if we're very unlucky, how many elements do we have to look at in order to either find the city or conclude that it's not there? And then the second part of that thought question is, can we do better? So to answer this question, I'm going to step over into the real world.
まあ辞書出すよな。
So I'm going to use a dictionary for this example, and this is a physical dictionary, which some of you maybe have never used in your lives, but this is what it looks like. It's an enormous book that has basically every word in this case, the English language in it. And I can find definitions of the word, I can find their origins, the spelling, so on and so forth. And so if I was going to find a word in this dictionary, here's an example of how I might use linear search to find that word. Let's say I'm looking for the word shark. So I open up my dictionary to the beginning. Let's see, okay, acrobatics, let's see, all right, not on this page. And over here, not there, acupuncture, nope, still not there. I'm looking. Are you getting bored yet? I'm getting very bored. I'm not going to make you watch me page through this dictionary page after page to find the word shark. It's way back here at the S's. This is going to take a really long time. But this is effectively what we were doing with linear search. We are starting at the beginning, looking all the way through in a row, our array. So what's a better approach to approach this problem? Well, it's an intuitive approach that we all use when we're opening a dictionary and trying to find a particular word. I don't open to the beginning because I know S is sort of in the middle towards the end of the alphabet. So I'm going to open sort of about halfway, maybe a little bit more. And I found myself in the R's. Okay, RS, S comes after R, so I need to go a little bit further. So I'll take another chunk of the dictionary and flip it over. Oh, I've gone way too far. I'm now in the Y's. So let me flip back a little bit. Okay, now I find myself in the T's. Keep going back. Great, I'm in the S's, S-O. I need to go back a little bit more. So on and so forth until I find the word I'm looking for. And already, after only about 3 or 4 flips, I'm much closer to shark, the word I'm currently looking at is shirt, than I was when I started the A's and was just flipping through one page after another. So this is an example of the binary search algorithm. What I'm doing is I'm starting with my entire pool of data, in this case it's the dictionary, and then I'm going to go halfway, and I'm going to reassess where I am to see if I found the thing I'm looking at. And if I haven't found the thing I'm looking at, I'm going to use some information to decide whether I should go to the second half or go back to the first half. And then I just have a smaller version of the same problem where I'll again flip the book open about halfway. So notice each time I flip, my pages are getting smaller and smaller and smaller, the number of pages that I flip. And that's the exact same intuition behind binary search. So let's step back over now into the code so we can figure out how to write this algorithm on the computer. So we're going to need to implement this algorithm by taking our data in our array, and what we want to do is be able to cut the list in half each time. But if you look at the list as it stands right now, you'll notice a really important difference between the data that's in this list currently and the data that we had over here in our dictionary. So think about it for a second, maybe pause the video, see if you can identify the issue that we have right now.
ソーティングしなきゃいけない。ということよ。順番になったら意味はないよねっていう。ABC 順になってないから。
All right, hopefully you saw it. the list has to be sorted. The reason that we can eliminate half the data in the dictionary is that the list of words in the dictionary is in sorted order. So if I'm looking for a word that starts with S, I know that nothing that starts with P or before matters to me, and I can just get rid of it. So the same has to be true in order to do binary search of the data in an array. It has to be sorted on the element that you're looking for. So in this case, it's sorted now by city name. And here's how the binary search algorithm is going to work. I'm going to start by identifying the string I'm looking for. Let's look for Beijing again. Notice Beijing is now at the beginning, towards the beginning of the list, because it starts with B. And what I want to do now is I want to keep track of what range of the array is currently active to be searched versus the part of the array that's kind of been ruled out. So I'll keep track of the active range of the array with two variables, a low index and a high index. And these are just going to indicate where in my array I'm allowed to look for my data. Outside of this range, I've already eliminated all the possible data outside of the range. So my range starts with the whole array, so low starts at 0, and high is length minus 1, in this case 7. And now I want to go to that middle element, just like I did in the dictionary. So I calculate the midpoint. I calculate the midpoint by taking the low plus the high and then dividing by 2. In this case, it's 0 plus 7 divided by 2. Now you might be thinking, oh, okay, the midpoint is 3.5. But the problem is that there's no position 3.5 in my array. Luckily, we're doing integer division here, and so we don't need to worry about decimal points or anything like that because Java will automatically truncate that 0.5 and give me the value 3 as my middle position. So 0 plus 7 divided by 2 is 3, and that'll be my mid. So now I'm going to look at the element that's at that midpoint. In this case, it's the element Essen, representing the city Essen in Germany. And I'm going to compare it to the string that I'm looking for. I'm going to say, does it match? Because maybe I found the thing I'm looking for. In this case, no, it doesn't match. But instead of just giving up, now I need to get some more information out of this element. Now I want to know which half of my array can I discard. Should I discard the lower half or should I discard the greater half? So I'm going to compare Beijing to Essen and see whether Beijing is smaller or larger than Essen. And I'm doing this alphabetically. So Beijing comes before Essen in the alphabet. So Beijing is alphabetically smaller than Essen, which means that everything that's larger than Essen in my array couldn't possibly be the string I'm looking for. So I can eliminate it. And the way I eliminate it is by adjusting my range to no longer include those elements. So I'm going to move the high point in my range to be one less than that middle element that I've just ruled out. So this is what it looks like. I will change my high to be mid minus 1, which in this case is 2, and that effectively rules out everything that's either 3 or greater. So now I have another version of the exact same problem. I have a low value, which is still 0, and a high value of my range, which is now 2. So I only need to look in this range of the array, and I'll do it the exact same way I did it before. I calculate a mid value, so 0 plus 2 divided by 2, which is 1. And then I'll look at the element that's at that position, in this case it's Beijing. I compare the city I'm looking for, Beijing, to the city that I see, which is also Beijing, and I see that I found a match. So that's great, I'm done. I can just return that 3-letter city code. And you can see that this was a lot faster than my algorithm before, which had to look through about 5 different cities before it found Beijing. Now, I recognize that Beijing moved now, so it's further towards the beginning. But in general, this is going to be a lot faster than our linear search algorithm, and we'll look at just how much faster a little bit later in this lesson. So here's our algorithm in that same pseudocode we used before to look at the linear search algorithm. We're going to now need to initialize 2 variables, which are the low and high end of our range. And again, we initialize low to be 0 and high to be the length of the array minus 1, which is the last position in our array. So we've got the whole array in our range. Now we're going to enter a loop. And it's a little bit unclear yet when our loop is going to stop. So let's leave that as a question mark for the future. That'll be for you to think about in just a second. But inside the loop, here's what we're going to do. We're going to calculate that midpoint of the array, and then look at the element that's in that midpoint of the array. If that element matches the city that we're looking for, then we're done. We just return that 3-letter city code. Otherwise, if the city is alphabetically less than the city that we're looking for, if the city we're looking for is alphabetically less than the city at the element that we found, we want to update our range so that we're looking at only the small half of the array by moving high to be equal to mid minus 1. Otherwise, we know the city that we're looking for is in the larger half of the array, in which case we update our low value to be equal to mid plus 1. That's what the loop does. Again, we don't quite know when it stops, but if it stops, what that means is we haven't found the thing we're looking for, in which case we can conclude it's not there, and we'll just return that value that indicates that it's not there, for example, the value null. So that's pretty much it, and the only thing left to figure out is, when do we stop that while loop? This is a question I'm going to give to you. So I want you to spend some time thinking about what should the while loop condition be. And there's going to be a quiz that is going to ask you a bunch of choices, and you're going to want to select the correct choice. And in order to do that, what I recommend is that you work through on your own several examples of cities that aren't in this list. So trace through that algorithm using the loop that never ends yet to figure out what the algorithm does and figure out when it makes sense to stop that loop. Talking about extremely large data. In the middle of that list, I see Montreal. Montreal is not equal to Istanbul. Istanbul is alphabetically less than Montreal, so I'll again adjust my range appropriately. Now I'm down to just one element. I have a range that includes only one element, so high and low are the same. But that's okay, that's no problem. This is still a valid element that we can look at. This element is Lagos, and it is not equal to Istanbul, so I again conclude that I need to move my range. And in this case, Istanbul is alphabetically before Lagos, so I'll change my high value to be 1 less than mid, in this case making it 3. But now I'm kind of stuck. If you look at the array, all the elements are grayed out, so I've effectively ruled out every single element in this array. So how can the computer know this? Well, let's look down at our low and our high values, and something kind of funny has happened. Low is 4, but high is 3. So our low has actually gotten to be greater than our high value, which indicates to our algorithm essentially that we've exhausted all of the range that we can look at. So we've squeezed our range so tightly that high and low have actually switched places, and we're out of places to look. So at that point, we can conclude that the element that we're looking for is not actually in the array, and we can simply return this null value indicating we didn't find it. Okay, so now it's your turn again. Go ahead and finish off this code. I'm showing you a skeleton code here for that binary search algorithm, and you can go back to the algorithm and compare it to this code. One thing I'll point out is this method compare to that you might not have seen before. What compare to does is it compares a parameter object to a calling object. In this case, it will compare the city that we're looking at, the city name that we're looking at in that airport object, to the toFind city name. And it will return -1 if the calling object, so in this case toFind or Istanbul, is less than, alphabetically less than, the city object in the airport, so the parameter object. It will return 0 if they're the same string, and it will return +1 if the city we're looking for, the toFind, is alphabetically greater than the city that we passed in as the parameter. So we can use that to make our choice about whether we should go look at the smaller end of the array or the larger end of the array, or if in fact we're actually done. So use that information to complete this code. Pause the video, and I'll pick up with you again in just a minute. All right, welcome back. Let's fill in this code. There's not too much you have to write. Just have to write what happens in those 3 conditions, depending on where the thing you're trying to find is relative to that mid location that you're looking at. So in the first case there, that if compares less than 0, what that's saying is the element we're trying to find, the city name we're trying to find, is alphabetically less than the element that we're looking at in our array. So we need to adjust our range so that it's in the lower half of the range we were previously looking at. That means we need to bring high down. So let's change our variable high so that it's down at mid, but not just at mid, it actually needs to be 1 less than mid because we already looked at mid. So we'll subtract 1 from mid, and that's our new value of high. And then the loop's ready to start again.
Yeah.
But if compare is greater than 0, that means the thing we're trying to find is alphabetically greater than the thing we're looking at mid. So we need to adjust our range up. In that case, we need to change our low variable. So we'll change it to be equal to mid plus 1. And if neither of those things are true, that means that compare is actually equal to 0, which means we've found the element that we're looking for. In which case, we can just return that 3-letter airport code. That's all we need to do here in the else statement is return airports at position mid dot get code. And that's it. That's the complete code. And there you can see it a little bit cleaned up. Now I just want to make one small comment about this code. Most people, if you show them this code, if they're sophisticated programmers, they kind of cringe. They'd say, oh, there's kind of a problem here. It's not really a functional problem. It's going to work correctly most of the time, except when your data is very, very large and your numbers for high and low get very, very large if your array is really, really big. What's going to happen is when you add high and low together, it's going to do something called overflow. You're going to get a number that's so big that you can't represent it essentially in Java in an integer value. So we can help guard against that situation by, instead of adding high and low together and then dividing by 2, what we really should be doing instead is subtracting low from high to get the range we're talking about, dividing that value by 2, and then adding it to our low to get it back into the correct range. So that's a better way to write this code. The other way will work as long as your numbers don't get too big, but to be a sophisticated programmer, start getting into the habit of thinking about things like this. You don't ever want your integer values to get too big when you can help it. So let's end going back to these same thought questions. So we said before, in a linear search, if we get unlucky, we're going to have to look through every single element in our array. And if there are a lot of elements in our array, like there are a lot of words in the dictionary, that can be a very, very slow, cumbersome process. So binary search is going to improve on that a lot. So you notice when we were tracing through the algorithm and when I was looking through the dictionary that I could eliminate essentially half of the remaining choices without even looking at them every step through the loop. That was great. And if I do this process repeatedly, what I'm doing is I'm dividing the number of things I have to look at in half every time. So I divide my original numbers in half, I have half as many. I divide that in half as many again, in half, in half, in half, in half, until I get down to just a single element that I'm looking at. And it turns out that the function that expresses that half, 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 half notion is the logarithm. It's the logarithm base 2. So if I compare the function that represents the number of elements that I have to look at in linear search, which is just equal to n, the number of elements that I have in my array, to that log base 2 n function, I can see that these two functions behave very differently. So when my n is fairly small, say 2, 32, 1024, my log is also quite small, but the two values aren't horribly different. But as n gets very, very large, you can see that a huge difference emerges between these two values. N grows, and it can get pretty darn big. So it can get into the billions. There are about 7.2, 7.4, depending on when you're watching this video, billion people on the planet. So if you think about that in terms of n, 7.2 billion, and log n, which really isn't that much more than 30, that's a huge difference. And so these numbers are really going to make a difference when we're talking about extremely large data. So that's our first taste of comparing basically how long these algorithms take to run. And you're going to see much more of that in the next couple lessons on sorting.
So one thing I really struggled with when I was learning arrays and sorting algorithms was array bounds. I was getting exceptions everywhere. I didn't know what to do because I was getting so many exceptions. And one thing that really helped me was when I talked to one of my professors. He told me to draw. Simply draw the array and make the numbers and everything, and go through each step of the algorithm and doing the sorting, the putting the indexes, and it was one thing that after that I didn't get any array bound exceptions, and it was perfect.
練習。ではいいんだよ。The following code implements an search that implements to search sources in a synthetic order. Choose the option that clarifies in the missing inline code. ファイルをさ、if to search to find the equals binary search です。あれ to search is such a line plus name as code. Jumps だと equals in the missing integer index. to find が、さあしたミッドした前の時に、だからさ、to find じゃん。これだな。どこじゃん、ちょうどミッドだよ。ヒント。今講義できかな。
In the previous videos, Christine talked about some algorithms for finding information in large collections of data. What you saw is if the data is organized, then it's easier to do some of these algorithms. So in this video, we'll talk about ways of organizing data, and in particular, how to sort it in some order. And then you'll see some advantages of having it sorted. So let's think back to binary search, which is one of those algorithms for searching that Christine presented. Remember that when we do binary search, at each step of the algorithm, we reduce the number of elements that we need to look at by half. And so, all in all, we look at about log n number of steps if n is the size of the list of elements that we started. Okay, so what we remember now is that in order for binary search to work, the data in our list of elements has to be sorted by what we're searching at. So for example, if we're looking for the country code, the airport code of Essen, then what we do with this particular list is we look about halfway through our list of elements and, oh, we found it, excellent, Essen is right in the middle. All right, so that's kind of silly. Let's look for another element. Maybe let's look for Beijing. Let's look for the airport code of Beijing. And so again, we start by looking in the middle of our list of elements, and then we compare Beijing with Essen, and we see that Beijing is alphabetically earlier than Essen, and so we only need to look at the first half of the list because we have the list sorted in alphabetical order. So the order is really helping us out here. Now, think about this order. Sorting means that we list our elements in some order that we've decided ahead of time and that is compatible with the search algorithm that we're trying to do if the sorting is done as a first step towards searching. So in particular, for this example, what we're trying to do is find a city name, and so we're sorting our data based on the first letter and then the second letter of the city. So we're sorting the city names in alphabetical order. Now, when you think about airports, the city is not the only piece of data associated with the airport. We also have a country that the airport is located in. And so it's conceivable that instead of sorting by city, we would want to sort our airports by, say, country. And so we'd want to organize the airports alphabetically according to country. There's nothing stopping us from doing that, but we have to think about why we want to do that. And so if we're looking for an airport in a given country, then it would make sense to sort all the airports based on the country name. And so that's why the sorting has to be compatible with the searching. Now, binary search, when Christine presented it, she showed you how it was absolutely necessary for the list to be organized in order for binary search to at all work. But before she talked about binary search, she already talked about linear search, which was this sort of simpler algorithm for looking through a collection of pieces of data to try to find one particular item. And with linear search, we didn't have to make any assumptions about how the data was organized. Remember that in linear search, we start at the beginning and we flip through one at a time, keep on going, looking for our particularly desired piece of information or piece of data. And that's fine. But actually what happens is if we happen to know that our information is sorted, then we get a performance payoff. So let's think about the array of airports in cities and countries, and let's think about trying to find the airport code for Istanbul, for example. What we might do in linear search is start with the first element of our array, Agra in India, and see, okay, that's not Istanbul, we have to keep on going. And then we go to Beijing, so that's not Istanbul, we have to keep on going. Chicago, Essen, Lagos. Well, if we were just doing linear search, we'd have to keep on going. Montreal, Quito, Sydney. And then only once we got to the end of the array, we would say, okay, Istanbul wasn't there. It's missing from our array. We can't do anything. We return null. But if we know that our array is sorted, we actually could have stopped a little earlier when I paused, right? As soon as we got to Lagos, we noticed that Lagos starts with L, which is alphabetically after I in the alphabet. And so if Istanbul was in our array, it would have to happen before Lagos. And so we don't have to look at the rest of the elements in the array to know that Istanbul is missing from this collection of data. And so what we get here is that if we do some upfront work, if we sort our array, if we sort our list, then in certain cases, our algorithm can run much faster. And we can have some logic built into our algorithm that says, if we're sure that our element that we're looking for is missing, we don't have to keep on going. We can stop right here and say, we've reached somewhere past the alphabetical location of where our element would be. We don't need to keep going. Okay, so far we've seen that sorting, which means arranging in order, can help us in both binary search and linear search. And there's actually another algorithm that is helped by having our data sorted. And so let's think about the problem of having a huge amount of information and we want to look for duplicates. Okay, you can imagine all sorts of use cases for this, but for that, let's abstract away all the applications and just think about how we would approach this question. And so if we're given a whole bunch of unorganized data, this might be kind of hard and we might have to loop through the list a few times and figure out if there's any two pairs in the list that are the same. But what if we were willing to pay some upfront cost and sort the information first? Well, then we just need to do one pass over the information after it's sorted and look at consecutive pairs of elements and see if they're equal, because the duplicates would show up right after another in the sorted list. And so in the data that we started with, we see that it's pretty quick to find that 84 appears twice once we've sorted the list. All right, so I'd like to leave you with a few questions. What we've done in this video is given a taste for the algorithmic questions that we think about when we're developing new strategies for solving problems. So when we have an algorithm like binary search or like linear search, we like to ask ourselves, for particular cases, how fast will this algorithm run? How slow will it run? How many steps do we need to take? And how lucky can we be? So can the data or its organization, the input from the outside world, have an impact on the runtime of the algorithm? What's it going to be like in the worst case? What's it going to be like in the best case? And also, when we're developing algorithms, sometimes we're willing to spend a lot of energy at the beginning if we're going to be able to reap benefits from that upfront cost by having the later algorithms that maybe we do a lot of times be much more efficient because we did some overhead initial work. So in the next few videos, we're going to be talking about algorithms for sorting, and hopefully now you understand why they're so important, because having sorted data can really help all sorts of follow-on algorithms.
Mia just had us understand about worst case and best case runtime of algorithms. Also, both can be important different circumstances. Which do you think is used more commonly in computer science? それはworst case よ。だから、ビッグソーとかいいとうんだとかって話になるんだよ。
So in this video, we're going to look at a specific algorithm for sorting data. And throughout the examples, we're just going to use an array of integers, but the same ideas and principles translate whenever we have information that's all of the same type, and we can compare pairs of information of that type. So by the end of this video, you'll be able to explain the selection sort algorithm and write code for it yourself. So let's get started, and let's think of a toy example. And it's always useful when developing algorithms to think of a specific concrete example that we can work through the steps of the algorithm with respect to this example, and then afterwards think about generalizing it. So let's think about this array of integers, and there's only 6 elements in this array, so we can probably do it in our head, but let's think about it systematically, how we would go about sorting these elements. And what we might do is, first of all, say, at the end, I want the smallest element to be in the first position in the array, the second smallest to be in the second position in the array, the third smallest to be in the third position in the array, and so on and so forth. And so let's look for the smallest element. So we're looking through our entire array, and we're looking for the smallest element. And lo and behold, we found it. It's 7. It's already in the first position. So we really don't need to do anything else to it. It's already where it's supposed to be. And so we don't need to ever think about it again. It's in place. It's done. And so now what we want to do is move forward and say, well, what about the rest of the elements in the array? What's smallest among those? Because whatever's smallest in the rest of the array is going to be the second smallest out of everything, and so we should bring it into the second position in the array. Okay, and so we have now 5 elements to consider, 1 less than before, and we're looking for the smallest element, and oh my goodness, we're lucky again. 16 is the smallest. It's already at the beginning. We don't need to do anything. Leave it in place. Okay, our problem is reduced further yet. Now we need to find the third smallest element overall, but that's just the smallest element in the remaining unsorted elements that we haven't thought about yet. And so we've got 4 elements to consider, and we want the smallest one. Now we see that it's 43. It's not the first one like we had in the previous 2 examples. And so what we need to do is to put it in its correct location as it would be in the sorted version of the array. And so we need to swap it with 66 in order to move 43 to its correct location. Okay, and so we go ahead and do that, and now 43 is in its correct location for the sorted array. We don't think about it anymore, and we move on to look at the remaining 3 elements, look for their smallest, 51, and now we move 51 to its correct location where it's going to be once the array is sorted, and so we have to swap it with 66. Go ahead and do that, and now 51 is done, and it's in its correct location. We don't need to think about it ever again. And we look at the remaining 2 elements, look for the smallest among those, that's 66, swap it, and now we're actually done, because for the last item, well, the only reason it's in the last position is because it wasn't the first smallest, it wasn't the second smallest, it wasn't the third smallest. It's already in its correct position. We can't compare it to anything else. And so when we've got to our last position in the array, we're actually done. We don't need to do anything. Okay, and so what that means is that we've got an algorithm, a series of steps that we can take algorithmically to perform this task. So we've got selection sort being described here as first find the smallest element and put it in location 0 in the array, then find the next smallest, put it in location 1.
Selection works left to right in array, and we are looking from the smallest. When the question is evenly done sorting, what can we say about the left half? ジェネレートハーフとアレイスタン。この二つが両方とも入るな。
etc. In the previous video, we developed an algorithm for sorting a bunch of pieces of data and organizing them in some order from smallest to biggest. What we'd like to do in this video is translate that algorithm or high-level description of the strategy into Java. So what we're going to do is think step by step about how to go from natural language descriptions of the strategy to actual code. And so let's start by thinking about what that strategy even was. And so we talked about selection sort. So selection sort has, as its general approach, first of all, we think about the smallest element overall in the entire array. And we look for that smallest element and we try to put it first, because that's where it's going to need to be at the end. And then we move on to the rest of the array, try to find the smallest element among those elements, and then put it in the second position overall, because that's its correct location at the end. And we keep going, and we keep going, etc. So let's think about how we can translate this approach to constructs that we know from programming. And so let's start by thinking about the big picture. And what we're doing in selection sort is we're looping through all of the positions in the array, and for each one of those positions, we're trying to find the true value in the sorted array. So for each position I, from the very beginning of the array all the way until the end, we're trying to find the right element to put in that position. But actually, not all the way until the end. Remember from the previous video, we talked about a small optimization that once we've sorted the first all but last elements of the array, then the last element is going to be in the correct position because there's really nowhere else for it to go. Okay, so we've got that little tweak, and the big picture here, what's important is that we've got a for loop that looks over each position in the array and tries to find the right element there. And it's also useful to keep in mind that as we're going through this algorithm, we have an invariant property, a property that never changes. And that's that once we've worked on position 0, position 1, position 2, then the elements in those positions are sorted and they're never going to change at all, no matter how many more steps we have to go or how big the array is. Those positions are done and the correct elements in the sorted array are already there. And so what we have is this array where slowly, we're organizing the first bit of it, and then we're focusing on the very next position, say position I, and looking for what element to put there. So let's think about the body of the for loop and what we need to do in that body of the for loop. And so a way to think about that is to look for the smallest element in the not yet organized piece of the array, and whatever is the smallest element among the elements of the array that we haven't put in their correct position, that's the one that's going to need to be in position I. So we need to find the smallest element in all of the elements that remain, and then swap it with the element that's in position I so that that element is in its correct location. Okay, so let's formalize a little bit what it means to be in the still unorganized or unsorted part of the array. Well, those are all of the elements in position I through the end of the array, length minus 1. All right, so as you can tell, we're getting a little bit closer to coding up the solution. And what I'd like you to do now is pause the video and try to write the code.
Are you using the help of I can step on the hey,だよね。わかりやすい。
Welcome back. Let's work through it together and see if the code that we develop is similar to what you did on your own. So you probably declared a method that is going to be called something like selection sort and takes as input the array of values that we want to sort. Now, in this method, the way that I've designed it, we're not going to return any values. So the return is listed as void, because what we're going to do is sort the elements of the array in place. So we're going to move them around in the array that we're given. And now remember that we have the outer for loop, and that outer for loop is looking at all positions I from the very beginning until the second last element. Okay, now for each of those positions, we had to find the correct element to put in that position. And so now we have to implement that piece of the algorithm. And so what we're going to do is try to find the smallest element that has not yet been put in its correct location. And so we want to keep track of the index of that smallest element, the location of where that smallest element is in the list. So at the beginning, we think, well, maybe the smallest element is already in its correct location in I. So our first guess is that the smallest element is in the first place that we look at, namely position I. And then we want to step through all possible positions in that unsorted part of the array and compare the elements in those positions with the value of the element at our current best guess for where the smallest element is located. So we're comparing the element at position index min with the element at position j. And if it so happens that the element at position j is smaller than the element at the position which is supposed to record the smallest element, well, we need to update what we think is going on. Now, in this case, we think that the smallest element is actually in position j. And then we have to keep on going and keep on checking all of the elements to make sure that index min really records the position of the smallest element in that remaining piece of the array. So once we've gone through this inner for loop, what we have is index min recording the position of the smallest element in the remaining part of the array. And then the last piece of our algorithm is to put that smallest element in its correct location, namely in position I. And so we might have a helper method swap that we define somewhere else, and that swap method looks at the array vals, and it swaps the element at position index min with the element at position I. And so what that would do is take the element that's supposed to be in position I and really put it there. Okay, and so what we've done here is we've gone from the high-level description of selection sort, and we've now gone ahead and implemented it using Java. All right, so before we leave this algorithm and say, whew, we've done it, pat on our back, we can stop thinking about it now, it's useful to probe further and always ask ourselves some questions. How do we know that this algorithm and this implementation always works, no matter what array we give it? And if we believe that it does work, how well does it work? And of course, as good engineers and scientists, we always want to do better. And can we? So in the next video, we'll talk about some of these questions. In the previous video, we implemented selection sort in Java, and then we stopped and thought about some questions to do with this algorithm and how well it performs. So far in this course, we haven't really asked ourselves whether algorithms are correct and how well they run, and so let's take a few minutes now to think about how we might even formulate answers to these questions. So let's think about correctness first. We had a problem, that of sorting an array, meaning organizing the information in the array. And then we had a candidate strategy, selection sort, that we think did pretty well, and we think that it really does organize the elements in the array. But if this was a really mission-critical problem that we are trying to solve here, it's not enough for us to just sort of say, yeah, I guess it's going to work. Hopefully there won't be any bugs, right? We want to be certain and convinced that our algorithm is really going to do what it's supposed to do, no matter what edge case we throw at it or how big an array we give it. And so let's think back to the high-level picture we have of selection sort and think about how that high-level picture can give us confidence that the algorithm works. So remember, what we're doing in selection sort is at each step through the for loop, we're looking at a new position in the array, and we're swapping into that position in the array the element that's going to be there when the array is really truly sorted. And so what we have is some initial piece of the array that is sorted and that keeps growing each time. And so as this sorted part of the array, the dark gray part of the array, grows with each iteration of the for loop, more and more of our array is in good shape. It's organized and it's sorted. And so by the time we finish the for loop and have gone through the entire length of the array, then our entire array is sorted. And so this argument that we just went through can be completely formalized and can be used to prove the correctness of selection sort. Okay, so we're convinced that it works, but how well does it work? And what does that even mean? And so the question of performance is a really tricky one, but a super critical one. And it makes the difference between a very sluggish computer that no one really ever wants to use because it takes seconds between when you click a mouse and when it actually responds, to a super snappy computer that everyone is really happy running apps on and maybe even multitasking. Because performance we can measure with time, we can measure with resource use, and the experience of how an algorithm runs makes a big difference to how far we can push that algorithm and how big a data set we can expect it to work on. So it turns out that selection sort, even though it's correct, doesn't do so well when we think about its performance. It turns out to be a very slow sorting algorithm. Now, we won't talk about the details of what it means for one algorithm to be slower than another and how we can compare algorithms when their performance might depend on their input in this course. But we will talk a lot more about it in the next course. And so stay tuned. It's a beautiful theory of computation and complexity that we'll get to in a little while. Now, what I want to mention, though, is that aside from performance issues, and somewhat motivated by performance issues, we're always on the hunt for other algorithms for solving even the same problem. So we had this sorting problem, and we had one solution for it, namely selection sort. But even if we didn't know that it was kind of a slow one and maybe not so great, we'd still be interested in finding other algorithms that solve sorting. And that motivation for finding other algorithms comes from recognizing that in the real world, different contexts might require different properties from our algorithms. Sometimes we might have a nearly sorted list, a list that is usually pretty organized, but occasionally we add on to it, maybe as new computers join a network or as new people join a team. And so we might want an algorithm that responds really well to almost sorted data and is really fast in that situation. On the other hand, we might have a context where our data is going to be coming from all over the place and is not organized at all, but maybe is not going to change too often. And so maybe we have a different algorithm that doesn't respond so well to dynamically changing data, but does really well even if the incoming information is completely unorganized. So even if one algorithm is often slower than the other, it might still be useful for other reasons if we know something about the problem that we're solving and the real-world context that we live in. In the next video series, what we're going to be doing is thinking about other algorithms for sorting and foreshadowing some of the other techniques that we'll be thinking about in the future courses.
Considering. Yes.
Hi, and welcome back to our module on sorting. It's time for another one of these concept challenges. You've already got a good feel for these. You know that you're going to try to solve the problem yourself. You're going to discuss this if you have other learners around you. You're going to watch our UC San Diego learners talk about the problem, and then you're going to see my explanation of the answer. So you've already seen how the selection sort algorithm. You know the selection sort goes for every element in the array and essentially looks through the unsorted portion of the array, finds the smallest value, and adds that to the next smallest value and adds that into the array. So if I have two arrays, is sorting faster on one or the other or neither? Go ahead and think about this and we'll come back.
We won't tell you whether this other is good. Don't it want that you stand there in the perspective. Even give you a chance to try the problems again. いや、正解になってるじゃん。
Hi, I'm Luis.
I'm Melissa.
I'm Gustavo.
Well, I think it would take the same amount of time because there is one for loop that iterates over the entire thing.
For me, I thought it would be answer A because why would you have to sort something that's already sorted? Wouldn't it take least number of steps, you know?
Yeah, I thought the same thing. Like, it's already sorted, but like the computer doesn't know that, so you have to go like to the end.
Now answer the question again. Cousera is それはな。もう一回。ああ、そっか。こっちか。総的に別にそういうのはないっていうことね。
Hi, I hope the UC San Diego Learner video was helpful. What we'll do now is just walk through both of these arrays and apply a selection sort to each of them. So in the first array, we're going to do a pass. We're going to look at all the elements, and we're going to see what the smallest element is. And this is going to require us to look at essentially 6 elements. It's going to require us to look at all 6. And then we're going to find that 7 is the smallest, and we're going to put 7 in the very first spot, which is where it is already. In the next iteration of the array, we're going to look at the second element in the array. And we're going to see what's the smallest element. We're now going to scan. We're going to look at all 5 of these. And we're going to find that 16 is the smallest and keep it there. When we move to the next element in the array, we're going to scan the remaining. So I'm going to have to look at all 4 elements here to find that 43 is in fact the smallest, and then I'll swap them. So 43 now moves into the place that 66 was at. I'm going to move to the next element in the array. And I'm going to look at this element along with the remaining elements to find the smallest element. It's going to take me 3 steps to find 51 as the smallest. And then I'm going to swap 51 and 66. In the next iteration of the array, I'm now going to be looking at 97. I'm going to have to look at 97 and 51 and 66 to find out that 66 is the smallest. That takes 2 steps. And now I'm going to swap 66 and 97. And then the last step of the array, I'm going to look at 97 to see if it is the smallest element of the remaining array. It is, and we're done. Now, that did seem like it took a number of steps because I was having to swap so many elements. But what's going to happen with a sorted array? Is it going to behave that differently? Well, with the assorted array, it's going to start at 7. And it's going to see, is 7 the smallest element? And it's going to look at all 6 elements again. It's then going to move on to 16. It's going to find the smallest element. It's going to have to look at 5 elements to do that. It's then going to look at 43, and it's going to say, is 43 the smallest? And it's going to have to look at all the remaining elements, finding that 43 is, in fact, the smallest. It's going to move to 51, do the same thing. It's going to take 3 steps. It's going to move to 66, take 2 steps. It's going to move to 97 and take 1 step. So we haven't done as much swapping, but we've essentially taken as many steps. And what this really leads us now to thinking about is how do we define faster? So we can see that both of these arrays essentially took the same number of steps. But is that how we define faster? Well, if you're looking at a high level, the same number of steps means they essentially take the same amount of time. Now, some of you may be thinking, well, wait a second. I think if you look at the really nitty-gritty details, you can see that swapping only sometimes happens, or maybe this if statement only executes sometimes and it doesn't execute other times. And now you're starting to argue about individual machine instructions. But what view do we want to have? Well, for the most part, we tend to have a really high-level view when we look at algorithms to say whether or not one is faster than the other. In this case, we'd actually say that these are going to run the same speed regardless of the contents of the array. But we're going to spend a whole bunch more time in the next module talking about defining performance, defining how to compare different algorithms, and we're looking forward to doing that with you then.
通ってるけど、やり方が分かる違うよ。
So in the
ですかな。
previous video, we talked about selection sort, which was one algorithm for sorting data. By the end of this video, you'll have seen another algorithm for sorting data, and we're going to play a little game. Instead of talking about the algorithm at the high level, what we're going to do is present some code that I promise you will sort the data, but what I'd like to do is work with you to figure out how to describe that code in high-level terms. And this is a really useful skill that helps with reverse engineering code and also working in big teams when other people are implementing different pieces of the code. And so then once we'll have traced the code and figured out what it does, we'll be able to describe alternate algorithms for sorting and compare their relative merits. So let's start with a code and let's see what we have here. So we're going to call this method mystery sort until we solve the mystery together. And at this point, there aren't a lot of comments to help guide us. We're just seeing some Java statements. And so let's see what we've got here, and we'll step through with a particular example. So we see that we've got a variable being declared, and we've got a for loop that does something and has an inner while loop. Okay. Doesn't help us so much so far, but let's work through an example. And again, it's really useful to work through some concrete examples when we're working through these questions to help guide our understanding. And then later we want to generalize, we want to think about the full generality, but first let's make sure that we understand what's happening at a small scale. Okay, so we're working with the array of integers that we talked about last video as well. So we've got 6 elements, and we're going to trace through and step through the execution of our mystery method to see what happens. Okay, so at the beginning, in our for loop, we are initializing the value pause to 1, and what's going to happen the first time we run through this for loop is that curInd, which you might guess means current index, is going to be initialized to the same value as position. And so what we see on the left of the code here is that we've got a memory model. So think way back to the earlier module, one of the first modules that we did in this course, where we talked about using memory models to help us reason through the changing values of variables as we run through code. And so we've got boxes for each variables, and at the beginning, each of those contains the values of the initial values of the variables, namely 1. Okay, now what happens is we look into the condition for the while loop and we see, do we have to execute the body of the while loop? Well, we're checking whether the current index is greater than 0. So yes, it's 1. And we want to check whether the array element at position cur index is less than the array element at position cur index minus 1. So cur index is 1. Current index minus 1 is 0. So we're comparing the numbers 7 and 16, and we're checking whether 16 is less than 7. It's not. And so we don't need to execute the body of the while loop. We go right back up to the top of the for loop after incrementing the pause variable or position variable. Okay, so now position is 2, and the cur index is initialized at the top of the body of the for loop to be 2. And again, we have to check the condition for the while loop. And we look, is the current index positive? Yes, okay. And now we want to compare the value of the array element at position 2 and compare that to the value of the array element at position 1. And basically look at what's happening here. We're asking whether they're in the correct relative position to one another. We're asking whether 66 is less than 16 or 16 is less than 66. And in the array as it stands right now, 16 and 66 are in the correct relative positions, so we don't need to do anything. All right, so far we haven't done much except for updating our helper variables pause and curInd, and we do that once more. Okay, we step up to the next execution of the body of the for loop, and so now the pause variable has value 3, and the current index has the same value of that at the beginning. And now we check whether the array element at position 3, which is 43, is less than the array element at position 2, which is 66. And it is. So 43 is less than 66, which means that these two array elements are out of order. They need to be swapped in order to be in the correct location relative to one another. And so that's what's happening in the body of the while loop. We're swapping these two positions. And we also need to update the current index variable. Okay, so we've swapped the two positions. Now we have 43 in position 2, we have 66 in position 3, and the current index is 2. And we go back to the top of the while loop and we check whether 16 and 43 are in the correct relative positions. They are. so we don't need to do a thing. In this execution of the body of the for loop, we increment, pause, we update curInd, and we go again. And now we're checking whether 66 and 97 are in the correct relative position. They are. Awesome. Keep going, update pause, update curIndex, and we check whether 97 and 51, the elements at position 4 and 5, are in the correct relative position, and they're not. 97 is greater than 51, and so what we need to do is we need to swap them. We update the current index, and now we check again, and what we're checking is whether 66 and 51 are in the correct relative positions. They're not, so we need to swap them and update current index. Okay, current index is now 3, 51 and 66 are in the correct relative positions, and now we check whether 43 and 51 are in the correct relative positions, and they are. So sweet, we're done. Okay, so what that means is at each point of the execution of the for loop, at each time we've gone through the for loop, what we know is that we've guaranteed that an increasing part of the array is going to be in sorted order. So if you think about what happens and what the array looks like at the end of the body of the for loop when pause equals 1, what we have here is that 7 and 16 are in their correct final locations. Okay, at the end of position 2, we have 7, 16, and 66 at the head of our array. Now these are not going to be the correct final locations of each of these elements. At the end, when we finish sorting the array, 66 is not going to be in that third position. But what we do know is that the first 3 elements of the array at this point are in the correct relative order with respect to one another. And so what we're doing is we're growing an array that is sorted, even though there might need to be some elements that get put into that array later on as we go through the rest of the algorithm. Okay, so at the end of the for loop, when we've got position equals 3, what we have is that we have a list of 4 elements that are in correct sorted order. Then we have 2 elements that we haven't worried about yet, and they may need to go somewhere and nudge some of these sorted elements around, but these 4 elements will never switch position relative to one another. Okay. So what we have here is a beginning of a description in higher level terms of what this code is doing. And this transition between looking at the code and being able to trace its execution one step at a time to being able to describe it in higher level terms is a really, really hard cognitive leap, but that is really important. And so it takes practice. Keep at it, work on it, and you'll see you get much better at it. And one of the key strategies for doing it is to take it little pieces at a time. Okay, and so what we're thinking about is we're thinking about this for loop where we're growing a piece of the array that is in relative sorted order. So it's sorted, and even though the elements in this part of the array may not be in their correct final location, which is different from what we saw in the previous video, by the way, they are still always going to be in the same relative order to one another. And then we're increasing the amount of the array that is in this relative sorted order each time. Okay, and so what's happening here is in order to increase the piece of the array that's sorted each time, within the body of the for loop, we're finding the correct location of the next element that we haven't thought about up until now, relative to the first I-1 elements. And so then we want to nudge it into the sorted part of the array, nudge, until it gets into its correct relative location, leave it there, and then all of a sudden we have a nice bigger part of the array that is sorted, and we can go look at the next element that we haven't looked at yet. So this is actually a well-known sorting algorithm. It's a mystery no longer. It's called insertion sort, and that's because we keep inserting new elements into a previously sorted array into the correct position relative to the other elements, and then this sorted part grows and grows. All right, notice that this algorithm is quite different from the previous algorithm that we talked about, the selection sort algorithm that we talked about in the previous video. And that's because in the insertion sort algorithm, we have the elements that we're taking care of, they get taken care of in a different way. We don't immediately put them where they're going to be and they stay in that position forever after, and we know their location in the complete array from that point on. Rather, we're looking at relative locations and relative ordering. And so we have two different algorithms, but they share some features. And so with each algorithm, as we go through it, we ask similar questions about correctness and performance. And similarly, we would want to compare the selection sort algorithm to the insertion sort algorithms and other algorithms as well as they come. So with insertion sort, the mystery sort that we were working through just now, how do we know that it's correct? Well, the argument that we were making before about the part of the array that is in relative sorted order growing and growing and growing until we get to all of the elements in the array, well, if we were able to make that precise, that would be a convincing argument that this algorithm is correct, because no matter what we start with, at the end we get all of the elements in the array in sorted order, and that's what we want. So then there's a question of, can we do better? And when it comes to algorithms, well, we always want to do better, but what does that even mean? And so the question of goodness of an algorithm has a few levels to it and has a lot of complexity to it. So the baseline lowest bar of goodness that we want is that an algorithm does what it's supposed to, that it's correct. Okay, both selection sort and insertion sort have met that bar. But then we might want more. So for example, we want to be able to tackle huge reams of data. And so we might want our algorithms to be really fast. And so we want to be able to process billions and trillions of pieces of information very efficiently. And so we need to think about, how do we measure the speed of an algorithm? How do we talk about its performance in terms of time in general? When we don't a priori know what our data looks like, we want it to be good for all sorts of pieces of data. And so that will lead us to things like worst case analysis and asymptotic analysis that you'll see lots more about in the next course of this specialization. I want to also mention that there are other measures of goodness of an algorithm. For example, we might not want to waste a lot of memory while performing the execution of an algorithm. And so we might want to be very resource sensitive and not use up a lot of space. And so there's a notion of space complexity that we would want to think about as well. And then we also might want to think about other properties that the algorithm could preserve or not preserve. So for example, if we want to sort a lot of data on different dimensions, so you can think back about the airport data, we want to sort first by name of country and then by name of city, then we would want our algorithm to behave in a way that's compatible with doing multiple pass sorting. And so we might want to restrict which algorithms we consider based on only those that have properties amenable to our use case. So goodness and can we do better are always relative questions relative to how we plan to use the algorithms. Algorithms are actual living, breathing objects you can think about. They don't exist in vacuum. We want to use them. And the measure of their goodness is only in terms of how we can use them and what they can tell us.
We will just allow the instance to detail and we will begin talking about how to measure algorithm efficiency. つまりアルゴリズムの効率性について考えることを。さて、suppose we run instance sort on the following arrays, instance sort from smallest to largest. Which input will take longer non-instance sort? Application, you can just count the number of which need to be made. いや、多分安定性の話なんだ。揃っていれば、例えば1でここですぐするからね、終わるから、ということだよね。で、Java の場合。
In the previous two videos, we've seen two different algorithms for sorting data.
つまりですね。プログラミングアサインメントが残ってるチェックエンジンのところでやるしかないってことだ。よし、行きましょう。
Now, that's just the beginning, the tip of the iceberg. There are many, many, many algorithms for sorting. We're not going to cover all of them. What you do want to keep in mind is that it's possible to optimize these algorithms tremendously depending on the application. And that takes a lot of work. But if you actually just want to use sorting, you don't need to write the sorting algorithm yourself. So by the end of this video, you'll be able to use the predefined Java method to sort, and you'll be able to explain the properties of this built-in method. Because whenever we use a tool, we want to be able to know both its functionality and its limitations. So it's useful to be aware of what the built-in method is actually doing. So as a reminder, we've talked about both selection sort and insertion sort. We talked about why each of these give correct algorithms for sorting data. And we also talked about some potential limitations in terms of the time that it would take for these sorting algorithms to actually work through a lot of data. And we've talked about how to write the code for these sorting algorithms. But we don't want to write that code each time. And so here's this code snippet of how we might be able to sort some data as part of a larger method without actually writing the sorting ourselves. We do need to use some built-in utilities from Java, and so that's why the import method is up top there. And then once we've built a list of, for example, integers, then all we need to do is call the sort method, collections.sort, on that list of integers. And then lo and behold, if you run this, you'll see that our numbers are sorted. And so it's this one-line method that is kind of a cheat because we haven't actually implemented sort method. But if what we're focused on in the particular method that we're writing is not the sort, but that's just sort of a helper piece of our code, then it's useful to go to the library and pick out that built-in method and use that instead of having to implement it each time. The reason it's useful is that we get the benefit of a lot of other people's hard work. Turns out that in this built-in method, what's being implemented is an algorithm called merge sort that's then been tweaked and optimized for various reasons. In particular, it's been made to be super fast, and we'll talk again in the next course about what we mean by a fast algorithm and how we can compare algorithm speeds to one another. But merge sort is known to be provably faster than selection sort and insertion sort in most cases that we care about. And in particular, it's really good for nearly sorted data. If you think back to selection sort and insertion sort, trace through how those algorithms would behave if our data was already almost sorted. And what you'll see is that one of them does better than the other in responding dynamically to the kind of data that's being presented. And so it's really useful if we know that we're going to maintain, for example, our list of airports, and every so often a new airport is going to come up and we want to add it to the list and then resort the list to make sure that it's in the correct location. We want our algorithm to be able to be responsive to that and be fast when our data is almost sorted and we just maybe have a couple of things out of place. The optimized merge sort that is also built into Java has an additional property in that it's stable. So that means that if we run sort a bunch of times on the same data, and we have a couple of pieces of data that are duplicates in some sense, they won't switch orders as we run sort again and again and again. And that can be useful if we want to, for example, sort the data on different dimensions. So what you'll see is in the project, you'll be using some sorting and searching techniques. But what we encourage you to do is to use the built-in sort and not have to rewrite sort on your own so that you can make use of these great properties that the optimizations have given us.
Which sort of is used by Java built-in sort method? Merge sort. Merge sort 基本的に安定してるのはコンペアラ。
In the previous video, we started talking about how to use the built-in sort that's available to us in Java. What I'd like to do now is to think about how to generalize that technique for more complicated objects. So by the end of this video, you will be able to define and use the comparable interface in Java so that we can have access to that built-in sort method. So if you remember last time, what we talked about is how to use collections.sort and then feed in a list of integers and somehow magically get the list returned to us as a sorted list. Now, what we observed happens when we use this method is that we're using the built-in merge sort. And the beauty of that was that we didn't have to implement merge sort ourselves. The issue, though, is that the list that we gave it was an integer list. So all of the values are numbers. But sometimes the objects that we want to sort, the data that we want to organize, isn't just numbers. Maybe it's more complicated objects. And so what we'd like to do now is think about using this built-in functionality, but for collections of non-integers. And so, for example, we might want to sort airports. So remember back to the beginning of the module and the motivating example that we've been talking about. We have an array of airports, and each of the array elements are references to airport objects. And what we'd like to do is to sort this array based on the city of the airport. Okay, so if we try to just go ahead and in our airport class define a method within the main method that just says, let's sort our airports. So we have an airports list and we're going to go ahead and sort it. Then we can hope for the best and try to compile this, but unfortunately, we're going to get a big old error message. And the reason for that error message is that airports are kind of hard to sort. We don't know how to compare two airports. So this is where the comparable interface comes in. And the comparable interface says, I will be able to give you access to merge sort and all of these other built-in functionalities like sorting in Java if you only tell me how to compare two object instances of your class. And so, for example, if we think about the object that has the city Montreal in Canada with a particular airport code and the airport object that we have that's initialized to the airport in Lagos, then we might want to compare these two and say M comes after L in the alphabet. And so when we're thinking about the city names, then the object that corresponds to the airport in Montreal should come after the object that corresponds to the airport in Lagos. On the other hand, we might want to organize our data based on country names rather than city names. And so then we might focus in on a different field and look at the instance variable for country. And in that case, we see that Canada, starting with a C, comes earlier in the alphabet than Nigeria, starting with an N. And so we'd want our objects to be organized a little bit differently. All right, so how do we do that and how do we tell Java this order? Well, if our class implements the comparable interface, and we say that by adding that keyword to the class definition, then our objects in that class will be able to be compared to one another. Now notice that special word that's after comparable, we've got the angle brackets and airport, and that's saying that we're specifying what kind of objects we're going to know how to compare. And this is using generics. Okay, so if we've told Java, we've promised that we're going to implement what's needed for a comparable class, what that's saying is that we have to fulfill the promise of the interface. And the interface comparable says you must implement a compare_to method. And the compare_to method has to be called by an object in that class. And it's going to tell us how to compare that calling object to an input other object. Okay, so let's think about how we might do that and think about what functionality we want. So we're going to return an integer, and that integer should demonstrate the relationship between the calling object and the other object. So if the calling object is supposed to be smaller than the other object, then the integer that we return is negative. If the calling object is supposed to be sort of the same size as the other object, then we should return 0. And if the calling object is bigger than the other object, then we're going to return a positive number. And so what you might think about is the comparison method is something like doing subtraction, subtracting the calling object minus other object. That's sort of the reference that we have for why these integers are returned the way they are. Okay, so what we'd like to do is to return some number when an airport calls compare to another airport. And what we're comparing to is using the city name. So we're going to have access to the city name instance variables in each of these objects, and we'd like to order those city names. But city names are just strings, and strings are objects, and strings can be compared because we can sort strings by alphabetical order. And so what we're going to do is really just be kind of lazy and say, someone else compare these two strings, and we just want to return the result of that comparison. So what we're returning here when we're comparing two airport objects is what happens when we compare the city name of our current object, the calling object, as compared to the city name of the other object. Okay, so let's try it out. Once we've implemented this compare to method, what happens when we go ahead and try to sort a list of airport objects? So we go back to the main method of our airports class, and we call collections.sort on the list of airports. And now, beautifully, we get as our output the list of airports in sorted order based on the city name. So Agra in India comes first, and then Beijing in China, etc., etc. Cool. One more thing. When we first thought about this problem, we said we can compare airports in some different ways. Maybe we can sort based on the alphabetical order of the city name, but what about the country name? So what do we need to do in order to change our compare to method in order to reflect the order of the country names? Well, we just need to change the body of that method to, instead of using the get country getter method for the instead of using the get city getter method for the city name of the airport, we're using get country. And that's really all there is to it. We just need to change that one line of code. And when we run the same collections.sort method in the main method of the airport class, all of a sudden our list is ordered based on the country names, and we have Australia first, and then Canada, and then China, etc. And so at this point, you're ready to dive back into the project and use the comparable interface and the compare to method to compare markers in your project.
You want to implement the compare method to markers in your project in adults. First, compare to return if the calling object is smaller than the parameter. A smaller compare to bigger はネガティブ。聞くのよね。だって次。オレンジック。
Hi again, and welcome back to our module on sorting. At this point, you've seen two different sorting techniques, so we're going to see how well do you really understand both of them. You're very familiar with the concept challenges at this point. You know the approach is you're going to pause, think about the question, answer it yourself, discuss it with people if you have them around you, watch a video of UC San Diego learners learning about the material, and then confirm your explanation with our explanation. So without further ado, if you look at these two arrays, in the top array we have the initial setup, and the array below that we've got the state of the array after 3 loop iterations. Which sorting algorithm could have been applied to reach this state?
インサーションショートだな。まだわからないよって。
Hi, I'm Melissa.
Hey, I'm Ken.
Hi, I'm Michael.
So for this one, I thought it definitely can't be selection start because the one will be at the beginning, right?
I was actually kind of confused in this question because I actually picked D. I thought it was both of them since like the first couple of elements are already sorted.
Yeah.
And we're sorting the elements. Shouldn't that be correct for both?
I'm actually pretty sure it's insertion sort because what happens is through the first iteration or the first loop, it checks the 4 and the 7, no switch, goes to the next 2 elements, 7 and 2, switches the 7 and 2, and then actually goes back and checks the 2 and the 4, the 4 and the 2, and makes that switch. And that would be 3 loop iterations, and that would be exactly what the bottom array is, and what she said, it can't be selection sort because the 1 would be at the beginning for selection sort.
And for the insertion sort, it never made
あ、
it
そっか、
to
違うんだ。ニーダーだ、バブルだ。あれということはやっぱインサーションでいいのか。
To reach this state. Hi, I hope the video with the UC San Diego learners was helpful. What we're going to do is just walk through both insertion sort and selection sort and see the state of the array after 3 loop iterations. With insertion sort, the key idea here is that you always keep the left side of the array sorted, but you're only looking at essentially the left elements. So the first pass, all you're going to do is look at element 4 and say, is 4 sorted? It sure is. Next iteration of the loop, it's going to look at 7. It's going to say, where should 7 be in relation to 4? Well, it belongs in the same place. So the third iteration of the loop now is where it gets interesting because it's going to look at 2. It's going to say, where does 2 belong relative to 4 and 7? And it's going to move 2 down all the way to the first place, and then 4, and then 7. So after 3 iterations of the loop, this would be the state of insertion sort. And this is what the question was asking for. So the right answer here is insertion sort. But let's talk through what selection sort would have done. Selection sort is always going to be looking through the remaining part of the array to find the smallest value and put that where we're currently looking. So with selection sort, you're going to be looking through the entire array at the start, and you're going to look to see that 1 is the smallest element. And then you're going to place 1 right at the start. Then you're going to look through the remaining part of the array, and you're going to find that 2 is the next smallest element. You're going to place that next. And then you're going to look through the remaining part of the array again. You're going to find that 4 is the next smallest element. You're going to swap that in. And this will be the state of the array after 3 iterations of selection sort.
テックやノーレージは、まあいい
so
で
it's
しょう。
time to get
ここは今度の次にして、今のソートまでの講義まででいいかな。難しいし。というわけで、今日はここまでにします。ている人はありがとうございます。今日は講義だけでしたね。
ディスコンネクト。